Now the next formula is 13.23, and that is coming from actually 13.24, and evaluate that those integral explicitly. And but the formula itself there is quite commonly used, and so we'll spend a little bit of time. So actually, it's the discussion of 13.24 first. Sometimes some people like actually use this formula. It's 1 plus z and gamma 1 minus z. Okay, and some people are not using 13.22 as the formula instead of using this as the formula. It doesn't matter actually. And uh, now this one you just go back to the integral to divide that using the integral, but then obviously you can extend it to all complex planes. So you're putting it in here, putting it in here. So z is either 1 plus z or 1 minus z. So you have a 1 here, so cancel with this one. So this becomes either z or minus z. Okay, so there's a product of two terms. One is z, the other is minus z in this factor, and this factor t. Okay, so your textbook changed one of them to s. So that is because I mean you have obviously you have two integral. You cannot use the same integral formula. So one is s to the z. So that's the first factor. This is becomes z, and then e to the minus s ds. The second one keeping t, and using this one, so you have a minus z is there. E to the minus t dt, and so you can combine the two and write like infinity ds dt, and combine this to become s over t with a z, and then e to the minus s plus t. Okay, so writing it like that, so basically just suggests you to do a change of variable. So the change of variable is following a textbook u is s plus t. So the exponential factor, this becomes u, and this ratio becomes v is s over t. Okay, so you can now change this integration, right, to uh, so basically ds dt change to du dv, but then there's a Jacobian, right? The Jacobian, I think your textbook using the inverse of the Jacobian. Uh, so partial u, let's see, d u dt du ds equals to partial u partial, not pure ds, sorry, dv partial s partial v partial u partial t partial v partial s partial v partial t. Let's see if I get the partial u partial s is 1, partial u partial t is 1, partial v partial s is 1 over t, partial v partial t is minus s over t squared. That equals to minus s. if you, I mean, we're taking actually taking the absolute value. So this become, because both have negative terms, so you just take the absolute value, becomes 1 over t plus s over t squared. So you can combine the two, becomes t squared, right? And then s plus t, and that becomes s plus t is just u, right? S plus t is just u, right? And t squared is uh, t squared is, I mean, you can use this t squared as you need to work out a little bit. So let's see, 1 plus v is equals to uh, 1 plus s over t equals to uh, 1 plus t plus s over t. So your extra t, because we need the extra t here. So 1, it means t square is, or t square in the denominator is 1 plus v square divided by s, t plus s square, which is u square here, is 1 over v square over u. Okay, so this is, I mean, I should say this is not, this is actually the Jacobian. This is not Jacobian. U, right? Basically, this is d du dv Jacobian. I should say dv equals to ds dv dt times the Jacobian, times this Jacobian, right? And so ds dt is du dv divided by this Jacobian. Okay, and so after all, so you can go back to here. So this is equals to, now change the du dv, right? J divided by du dv. I should say what is du dv and divided by j, which is u divided by 1 plus v squared. And then the rest is, this is v to the c power e to the minus u. Okay. And obviously, you need to convert the limit also. So you can, I'm just writing it at first because we haven't figured it out. Original is s over s and t, right? S and t. And all this u is s plus t, so this is u is constant, like all these diagonal lines. So this is u is, so u is 0 obviously in here. So like if u is 1, then this would be s is 1, t is 0, or uh, s is 0, t is 1. So this 1 and 1, 2, 2 altogether. So u is 1, 0, 1, 2, 3. So you have all this line. The ratio is s over t is just all this radio. all this ray going out from the origin, right? All this v is constant. Obviously, v is zero is this point, zero. And then the vertical line is v equals to infinity, right? So altogether is u goes to zero to infinity. So you have all this diagonal lines and all this ray coming from uh, the horizontal line to the vertical line is v from zero to infinity. So that limit covers the whole this quarter, this quadrant, right? So that is the integration area that we'll do. Okay, and then the good thing is this is now separate. It is separate form, so you can integrate u, which is supposedly trivial. Uh, u minus u du. Because that I think you can do it just by integration by part, and then the v1 v c dv 1 plus v square. This so this one is integration by part, right? Because e to the minus u is d du to the minus sign, so you have minus u d. I mean, not d. What's that? Just e to the minus u, 0 to infinity. Right. That's the boundary term. So at 0 is 0, at infinity is also 0. So boundary term is 0. And then minus, but then you already have a minus sign here, and plus, and then the derivative of that becomes 1, and then e to the minus u du. This is integrated e to the minus u divided minus sign, so basically flipping the sign. So 1 minus 0 is 1, so this is 1. So this factor is 1. The complication is this factor. I think we, in chapter 11, in the complex variable chapter, that kind of integral, I think we have an example or exercise doing something like that. And because of there's a z in here, so depends on whether it's an integer or not. For integer, that becomes elementary. But if this is not an integer, so we there's a branch point at v equals to 0. So there's if you complex v plane, so there's a branch point at 0. So this kind of integral we use whatever the formula that the contour we discussed going to here, going back to here. So that kind of a common contour that we use and to evaluate that one. And that can be done, but we're not doing it here. So that is gives you, but the final result is pi z over sine pi z. Okay, so that is fine. Okay, so that you just need to trust that you actually get to this formula, right? All right, and now you combine this with that, so combine this one equals to this one equals this one equals to pi c and then times 1. So the final formula is this yeah, 1 by c gamma 1 minus c equals to pi c sine pi c. Okay, so So that is one formula that people like to use. And if to get to the formula in a textbook, you just use the fact that one gamma z plus one is z times c times gamma z, and then so you can gamma z gamma one minus z. Just divide z over the other side, get rid of this z. Pi equals to pi over the sine. Let's see. Okay, so this is the formula. All right. So there's a lots of property, but uh, that one is more commonly used. So we discussed it a little bit more. So basically, that will give you uh, another relation. This actually like a refraction. You have z, and the refract about z equals to 1 point. So once you have z, you can get gamma 1 minus z. So that's so-called refraction formula. So that gives you another way to calculate the unknown gamma, unknown gamma function values from known values. Okay, and so that's another use. Another formula that is not as commonly used is 13.27. Let's, c plus 1/2. That's so-called duplication formula, gender duplication formula. The form is quite complicated for a non-integer for real number z. And but the proof of that, or the derivation of that, is actually using the beta function that we'll talk about in the section 3, right? But the one trivial value is for z is integer. For z is integer, this is just a factorial. And for z is integer, this is just a half integer formula, which we divide the formula. And this is, for c is integer, this is also integer, this is also a factorial. And this is just becomes 2 to a certain power. And that these two factorial can have, you can divide these two factorial. And then ultimately you get something that's what we discuss in here, this formula. Right, so of the half integer gamma function formula. So you can check that right away. Okay, but that's but for real z, we can come back to that using the beta function. So we'll not talk anymore about that. And what else in this? There's a discussion because we have a simple pole, or the gamma function has all the simple pole. You can either see that from the limit, infinite limit, or from this formula we just derived, because 1 over gamma have all these factor of 0, because obviously z equals to all the z equals 0 is 0, z equals to all the negative integer. One of these factor will be 0, so that's 0. Infinite many 0 of 1 over gamma. So one gamma has this pole, infinite many poles, and to calculate the residue of the poles is quite trivial, right? And in 13 point, you just use a simple fold formula, and you can divide the residue for I think it's z equal to negative n. Z equal to negative integer is finally is minus 1 to the n factorial, to n power to n factorial. You can derive that quite easily using the simple pole formula that we talk about. So we won't go anymore for that, because that's just a two minutes thing to talk about. And the next thing is this Schlaefli integral, the representation of gamma function. So this is 14.29. It just basically mentioned the contour. This contour Z, right? This this looks like the integral formula, except that there's absorbing the one factor in the definition of the and in the writing of your gamma function. This 2 pi I. I don't know why your textbook changed it to nu for this um, particular formula. Gamma, because he's always use Z, but then it's changed to nu. But it's just changed. But anyway, it's just the same. You should change Z, nu to Z. It doesn't matter, right? And so that's formula. Again, we won't derive that. It's just very straightforward. Just use the integral formula. This, but the Z contour is on the complex plane. This is complex T plane. It's coming from infinity going around. If nu, this value of all the previously called Z, if this is an integer, that's a branch point, right? It just go around. I mean, you can write a little circle, but that doesn't matter. It's just going around and then go back to the past the infinity of T, real T. That's the contour C, right? All right, and so that's the definition. You can derive that using the what we did for the complex variable, complex contour integral. And one thing is that this formula, if nu is integers, that becomes zero. This factor becomes zero, right? Right. So, I mean, one way to do it is because with the integer, this becomes the branch point. You get rid of the branch point, so obviously that can also be zero. It depends on whether it's positive or negative. Right? For all the positive new integer, that becomes zero. So you have zero divided by zero. You need to take the limit and to get the gamma function. And for negative integer, that is still zero, but then the negative integer, this becomes a pole. And you can evaluate that by the residue theorem. And that one is zero. So for negative integer, this is the gamma function becomes infinite. So it's singular. Okay, so that's one way to write it in this integral. Your textbook didn't mention the other one. If you look up a math textbook, you might encounter the other formula. This is called the Hankel's contour. Hankel's contour. Hankel contour integral, but it's actually considered this 1 over z, just like what we did for the other form. 1 over z, because it's an entire function, it has some nicer property than the inverse. I have a 2 pi, the same kind of contour, minus t to the minus z e to the minus t dt. Okay. And for this one, it's applied to any z other than infinity, obviously. Any z, you can apply this formula to calculate 1 over gamma. Okay, so that's another similar kinds of integral that you might encounter. All right, it actually exists. I mean, you can see that for many physical problems. In fact, I used that in my dissertation, PhD dissertation also. Somehow you can find some situation you can convert that to a gamma function. All right. So that is the topic, saliva integral. Okay, I think that's all. That's all. There's a there's an example, 13.1.1. It says uh, just show it and it's very kind of like a trivial example of like a, in statistical mechanics or kinetic theory, just do an integral of a distribution function. And sometimes if you express the integral variable as the energy, then that becomes the form of the gamma function. So you can integrate that using gamma function to that kind of like trivial. So you don't need to go through that. Right. Well, that's a long section. And still there's many more property of gamma function that some of them are listed in the exercise. I don't think I assigned too many of them, but if you want to know more properties, look up a math handbook.